So here's some practice for you. Go ahead and try these 8 problems out. Some are going to be perfect square, sum of perfect squares, which remember is prime. Some are going to be difference of perfect squares, which you can factor. Some may be neither. One hint, remember, the way you start any of these problems is to look for something common, because you can always factor. A polynomial is not prime if you can take something common out, because it does at least factor once. So try these out, pause the video, then come back and I'll throw up the answers. All right, so let's look at these answers. The first example, y squared plus 4, they're both squares, but it's a sum, so this is prime. In my next example, 4x squared is a square, 49 is also a square, and it's a minus, so this should factor 2x times 2x, so I'm square rooting the 4x squared. 49 is 7 times 7, and I need one of each sign, a positive and a negative. Since it did factor, we should always check. 2x times 2x is 4x squared. Outside is negative 14x. Inside is positive 14x. And the last term is negative 49. There's a positive and a negative middle term, so they add up to 0. There's where we started. So we had one sum of squares, one difference of squares. Let's look at the next one. In the next example, my initial thought is, oh, it's not a perfect square, neither is 45. But when you look at that 5 and the 45, hopefully, remember, think common factors. There is a common 5 there. So take the 5 out first. When we take a 5 out, we're left with x squared minus 9. And what we see inside here now are perfect squares with the minus, meaning that's a difference of squares. So we can keep the 5 and then factor this x squared minus 9 into x plus 3 times x minus 3. So there's our conjugates. But you had to factor the 5 out, the common factor of 5, before you could see that. To check this, remember, if we have three factors, make sure you multiply the 5 or the common factor out to the first one first. So 5x plus 15, and then distribute or FOIL that to the final factor of x minus 3. So foiling 5x times x is 15x squared. Outside terms would be negative 15x. Inside terms is positive 15x. And last terms would be negative 45. So these two middles go away, and I get 15x squared minus 45. That's where we started. Next example, 3x squared minus 48. Once again, there's a 3 in common. Our last example had a 5 in common. Here's a 3. If we take it out first, x squared minus 16. Now we do have a difference of squares because x squared is x times itself, 16 is 4 times itself. So because it's a difference, we can factor that into conjugates. X plus 4 times x minus 4. Checking that, again, multiply the common factor in first, 3x plus 12 times x minus 4. When we FOIL this, we get 3x squared minus 12x on the outside plus 12x on the inside minus 48. The two middle terms are exactly opposite signs, so they're going to add up to 0. So 3x minus 48 is where we started, and that's our answer. All right. Next example, 9x squared plus 36. And you might say, well, those are both perfect squares, but they're a sum. And you might say, well, a sum of squares won't factor. Well, you are right. A sum of squares won't factor, but look carefully. Remember how we've had a common factor in our last two examples. Is there a common factor here? There is. There's a 3, but there's also this 9 is common to both these terms. So if I take the 9 out, I have x squared plus 36 divided by 9 is 4. So I'm able to take that 9 out. So this is not technically prime because I was able to factor the 9. What's left, however, won't factor any further. So x squared plus 4, because of the plus, that's going to be a binomial that won't factor further. So therefore our final answer is just what I had here, 9 times x squared plus 4. We cannot factor further. Once again, it is not prime because we did factor the 9. Next example, x squared minus 9x. The x squared is a perfect square. The 9 by itself would be, but there's an x there. Here's a hint. Both these terms have an x in them. That's a common factor. So before you do anything else, you should take that common factor of x out. So when you pull x out, you get x minus 9 left. If you take a look at what's left here, the x is no longer squared, so you can't go any further. So this is as far as we can go. In these last two examples, I forgot to mention checking this last one, all you really do to check these two examples is distribute, in the first example, 9 back in. So we get 9x squared plus 36, which is where we started. And the check on this one, distribute the x back in, x squared minus 9x. So that checks. All right, two more examples. 25x squared minus 16y squared. Again, look for something common. Nothing common there. 25 and 16 don't have any common numbers other than 1. They are both squares, and it is a minus, so this will factor. 5x, make sure you square root not only the 25 but the x. That's going to go to both positions. And with 16y squared, you're going to use 4y in both positions. And then remember 1 of each sign. So that should be our result. Check that. 5x times 5x is 25x squared. Outside would be negative 20xy plus 20xy minus 16y squared. Two middle terms add up to 0, so that checks. All right, our last example has something kind of fun in it. X to the fourth minus 81. Now 81 is definitely a perfect square. It's 9 times 9. X to the fourth you might not think of as a square initially, but it turns out any even exponent, it's like 4, 6, 9, is a perfect square. Think about breaking it up exactly. So x to the fourth, if you pulled it apart exactly, which is what you're doing when you square root, would be x squared times x squared. The 81 pulled apart exactly would be 9 and 9. Remember, because it's a difference of squares, you're going to use conjugates, 1 of each sign, positive and negative. So that's where we would start. And the reason I say start is that notice there's still squares in here. X squared plus 9, those are both perfect squares. But because I'm adding them, I can't take this factor any further. But if we look at the next factor right here, x squared minus 9 is the difference of squares. So I can actually factor that one further. So I keep my first factorization and then factor this guy further. So x and x, when I square root the x squared, 3 and 3 for the square root of 9, 1 of each sign. So there's my final result. X squared plus 9 times x plus 3 times x minus 3. I'm a little bit out of room, but to check this, you could multiply from left to right just fine, but it turns out you can also, I haven't been doing this much, but you can also multiply in the other order, and that might be easier on this one. Multiply out the x plus 3 times the x minus 3 first, and then multiply that answer back to the x squared plus 9. So either way, I'm just out of room here, so I'll leave that check for you.